This is lecture 11 in BBSP 610. Today we're going to be discussing sample distributions and the central limit theorem. Again, I will apologize in advance that it's a little bit technical, but I'm trying not to go into the theory any more than what's really necessary, but understanding the basics of theory is important to understand why the normal distribution is important and why we can use it. So let's talk about the difference between x and x bar, and unfortunately it looks like the bar on my x's disappeared when I converted this to PowerPoint. I apologize for that, but the distribution of the population x would be the income of a given individual that you select from the population, or their SAT score, the weight of an individual mouse, whatever. But if you talk about a distribution of the sample mean, if you selected 100 people off the street and took their incomes or SAT scores or whatever, that will have a different distribution than the original x. As we discussed briefly in the previous lecture, it will have the same mean as the original population x, but it will tend to have smaller variance. And I'll illustrate this in more detail through the course of today's lecture. So for example, this is a data set that's built into R. Let's say that we measure the heights of 85 Loblolly pine trees. Say we want to make inferences about the distribution of the original data uh, and the distribution of the sample mean. So here's a histogram of this data set of Loblolly pine trees. As you can see, the distribution is clearly non-normal. There looks like these trees were selected from several different groves, so there's several different peaks in the distribution. We certainly don't see the nice bell-shaped distribution that you would expect from normally distributed data. If we take a summary of the heights of these loblolly pine trees in R, we see that it has a range from about 3.46 to 64.10 feet. I believe the units here are in feet. And roughly symmetric, but clearly non-normal due to multiple peaks. So the distribution of the original data x is non-normal. Let's say we want to calculate the distribution of x star, the sample mean, and let's just say we collect only 4 trees, take the average of those 4 trees, and we'll repeat this multiple times. So this gets a little bit confusing here, but the original data has a certain distribution. If you draw a single individual from the population, it will have a distribution corresponding to the histogram I described earlier. But if we select 4 trees and then take the average of those 4 trees and then repeat it multiple times, we take one set of 4 trees, then take another set of 4 trees and repeat this over and over again. Let's try that repeatedly and look at the distribution of x bar in this case. I did this in R, and here's what the resulting distribution looks like, and you can see already it looks a lot more bell-shaped than the original data did. And we'll see here in a few minutes that this is not a coincidence. And we can compute the summary statistics for x and x bar as well, that in the R code here, height is the original data, and x dot bar dot 4 is when I randomly selected 4 trees, took the mean of those 4 trees, and repeated it 85 times. So the sample size is the same as the sample size of the original data. And this x dot bar dot 4 was what I plotted on the previous slide. In any event, you can see that when I take samples of size 4 rather than samples of size 1, i.e. individual observations, then the mean and median remain about the same, but you'll notice the range is smaller when I take samples of size 4. The minimum mean of 4 trees was 8.67, the maximum was 60.37, slightly different than what we saw from the original data. And you'll also notice the first and third quantiles are much closer to the mean and median than the original data as well. If we take the standard deviation of a sample of size 4 looks like it's about half of the standard deviation of the original data. Oh, I guess I already said most of this. The mean of x is approximately the same. The extreme values went down. The standard deviation of the original data is larger than the standard deviation of x bar, and the histogram is much more bell-shaped. So let's try this again with samples of size 10. Here the distribution is looking nice and bell-shaped, and if we compute the summary statistics, we see the same trend, that when you take samples of size 10, the mean and median are about the same, but the range and the quantiles are both closer to the mean and the median. The standard deviation is noticeably smaller. And when we take samples of size 30, well, it's the way R drew this graph. If anything, it looks slightly less bell-shaped. That's due to the fact there's just more bends here. That, in fact, it's getting closer and closer to a bell-shaped distribution as the size of the samples that we draw increases. So again, we'll compare the distribution of x to the distribution of x bar, and we see the mean and median again stay about the same, but the standard deviation and range of the data are going down. So in general, the association between the sample size n and the distribution of x bar, we see that as n increases, the mean doesn't change, but the dispersion, i.e. the standard deviation of x bar, goes down as the sample size increases, and the distribution of x becomes more bell-shaped. Again, I apologize, things got messed up when I converted this to PowerPoint. The sample sizes should be visible on this table. It's 1 in the first column, 4 in the next, 10 in the third column, and 30 in the final column. And if you'll recall from the previous lecture, I gave you this result that if you take the expected value of x bar, that's equal to the expected value of x, and the variance of x bar is equal to the variance of x divided by n, which is consistent with what we saw in the previous table, that in this table, SDY on the bottom row is the standard deviation I actually got when I calculated this using the data. The top row is the standard deviation of the original x's divided by the square root of the sample size. As you can see, they're almost identical, indicating that this result is in fact correct. And the fact that the histogram of the sample mean was looking more and more bell-shaped was not a coincidence. This is probably the most important result in statistics, known as the central limit theorem, which is that if you draw a sample of n independent observations from any population with mean mu and standard deviation sigma, then for large n, the sampling distribution of the sample mean x bar will be approximately normal with mean mu and standard deviation sigma divided by the square root of n. The important word here, highlighted on this next slide, is that this works for any population whatsoever. That no matter how non-normal your data is, no matter how skewed it is, no matter how many outliers it is, no matter how bad your data is, if you average your data, you end up with something that's normally distributed. Mathematically, it is possible to find cases where this breaks down, but in practice, you'll probably never see them unless you're deliberately trying to do something strange. This raises the question of how large is large. That if your data is already approximately normal, n equals 10, maybe even n equals 5, if you average, in other words, if you average 5 or 10 observations, the central limit theorem should already apply. If your data is skewed or has outliers, you may need around 20 or 30. If your data is incredibly skewed, has tons of outliers that haven't been removed, and basically you have the worst data ever, then maybe you need like 70 or 80. The bottom line is that you don't need large samples for the central limit theorem to work. You'll get good results for even relatively small samples. And this slide shows another computer illustration of this, that the original data was simulated to be highly skewed with the density that you see in the upper left-hand corner of the slide. You average 2 observations from this highly skewed distribution. It's already looking reasonably bell-shaped. You get to 10 or 25, and it looks almost like a perfect bell curve. Another important thing to keep in mind from the statement of the central limit theorem is these n observations have to be independent. That if there's a correlation between the different observations you draw, you are dead in the water. That, for instance, if you took 10 people off the street and took their average height, the distribution of that average should be approximately normally distributed. If you took 10 people, all which were children of the same father and mother, those would not be independent observations, and the central limit theorem wouldn't apply here. And in practice, well, I should put the caveat, it does still apply, but the formulas that I gave you for the mean and variance will no longer work. And in practice, this assumption of independence is the one that's most likely to get you into trouble. We won't discuss the case where they're not independent. That gets really hairy really fast and is difficult to use in practice. For the purposes of this class, assume that they have to be independent or you're going to have problems. So for large n, x bar is approximately normally distributed with mean mu and standard deviation sigma n. So an important term to keep in mind is the quantity sigma divided by the square root of n, or in practice you take the sample standard deviation s divided by the square root of n is defined to be the standard error. The standard error you can think of as the standard deviation of the sample mean. As we've discussed earlier, the sample mean has the same mean as the original population, but smaller standard deviation. The standard deviation of the sample mean is what's known as the standard error. So, an example of how you would use this central limit theorem in practice. Let's say that you work at a hospital and you know that the birth weights of newborns in this hospital have a mean of 112 ounces and a standard deviation of about 20 ounces, 20.6 to be precise. And let's say that birth weights are not normally distributed. We know this is true in practice. It has a very strong left skew due to premature babies. So what's the probability that a random sample of 10 babies has an average weight of greater than 126 ounces? The first thing we do is compute the standard error. We know the standard deviation of the general population is 20.6. We divide that by the square root of 10, we get 6.51. So the average of 10 babies should be approximately normal with mean 112 and standard deviation 6.51. So drawing the picture here, the probability region of interest would be the red region in this graph, the area greater than 126. So to calculate that probability, we can use p-norm as we did in the previous lecture. That, in this case, it would be 1 minus p-norm, because we want the area greater than 126, with mean 112 and standard deviation 20.6 divided by the square root of 10. That turns out to be about 0.0158. Quick note in R is that square root of x, SQRT of x, give the square root. Square root of 4 is 2, etc. So let's do another birth weight example. Let's say that we want to find the probability that a sample of 10 babies has an average birth weight between 112 ounces and 126 ounces. Again, that would be the region on, again, that would be the red region in this graph here. You can calculate it using p-norm. The p-norm 126, 112, 20.6, that would be the area to the left of 126 minus the area to the left of 112. We end up with a probability of about 0.4842. Let's say we want to find confidence intervals for the birth weight of 10 babies. If you remember from the previous lecture, 95% confidence interval is an interval chosen such that there is a 95% probability that it contains the true value of the mean. So you can just find the 2.5%, 97.5% quantiles of the distribution. And we know the distribution of the birth weight of the babies. Again, it has mean 112, standard deviation 20.6 divided by the square root of 10. So we can use the Q-norm command. The 2.5% quantile is about 99.23. The 97.5% quantile is about 124.77. That would be the 95% confidence interval. And it's worth pointing out that the formulas that I've given in the previous slide only works if the population standard deviation sigma is known. In practice, this is almost never the case. How can you know the standard deviation if you don't know the mean? Well, luckily there's a little mathematical trick to get around the issue, which we'll be discussing in upcoming lectures. Now, a couple mistakes you can make with the central limit theorem. Let's say that you want to find the probability that a single baby chosen at random has a birth weight of 126 or greater. And you might want to just use the R command here, where you take 1 minus p norm 126, 112, 20.6. That will not work in this case because the underlying distribution is not normal. The population is left skewed. Now, I know we did this in the previous lecture with the example of the fish. We assumed the distribution of the fish lengths are normally distributed. In this case, the distribution of the original population is not normally distributed, and in general, that's a dangerous assumption to make. So you cannot apply the central limit theorem to a single observation, and it gets a little dicey when you take average of even small numbers of observations. And here's another example of when you can get into trouble if you apply the central limit theorem mindlessly. That this is a data set that's built into R. It has data on the closing prices of the French CAC stock market index from 1991 to 1998. It had an average closing value of 2,228 with a standard deviation of 580. So let's say we randomly select 100 days at random and take the mean of those take the mean closing price for those 100 days. That should be normally distributed with mean about 2228 and standard deviation 58 if we just naively apply the central limit theorem. So I randomly selected a 100-day interval from the time period in question. The mean value of the index during this 100-day interval was 2,904. So what's the probability that I managed to randomly select a 100-day interval with a mean of 2,904 or greater, assuming the true mean is 2228 with standard deviation 58 as I calculated on the previous slide? Well, I plug that into the p-norm command in R, I get a value of 0. The true probability isn't exactly 0, but it's ridiculously tiny. Like, we're talking like 10 to the minus 100 or something like that. I'd stand a better chance of winning the lottery several times in a row. The problem here is the observations are not independent. and I took a sample of size 100 from a time interval when the stock market was doing well. If the observations are correlated, then each individual observation provides less information about the true mean. In this case, the true standard deviation of a sample size 100 is much greater than 580 divided by the square root of 100 because the independence assumptions are not satisfied, so the distribution of the sample mean is much larger. Again, I won't go into the details of that in this class. Suffice it to say, you cannot simply apply the central limit theorem if the observations are correlated. The things to remember today is the sample mean x bar has a different distribution from the distribution of an individual data point, and if the observations are independent and is sufficiently large, the sample mean x bar will have a normal distribution, and knowing the distribution of x bar, you can make inferences about the true mean. In order to do this, though, you need to make sure that n is large and the observations are independent. If either assumption is not satisfied, this will give incorrect results.